Hi, my name is Tachapon Saranurak. This paper is about a simple deterministic algorithm for computing edge connectivity. So in this classical problem, you are given a graph G with n vertices and m edges. And what you want to compute is a cut S such that the number of edges crossing a cut is minimized. You call this cut a min cut, and the cut size of the min cut edge connectivity. We denote it by lambda of G. So this problem is very well studied. It has been studied using many different techniques. And in this talk, we will focus on the case when graph G is a simple graph, unweighted, and also undirected. Also, we will just try to compute edge connectivity, the number edge connectivity itself, and because it's just easy to extend it to compute the cut also. So let's focus on the simple case. Now the state of the art of the min cut algorithm on simple graph is as follows. It starts with a breakthrough algorithm by Kawarabashi and Thorap that give a near linear time algorithm and make it deterministic. In this work, uh, I will show an algorithm that is deterministic and is simpler than the previous deterministic algorithm, at least conceptually simpler, because it just takes a few simple steps. Once you are given something called expanded decomposition, however, the time is slower. But I hope that it's still nice to see because it's quite simple. Okay, all of these algorithms are using the following framework, which is called, which I just call it the min cut preserving contraction. This is the thing that is introduced by Kawarabashi and Laura. It's a very cool thing to know. So what is it? So given a graph, they said that there must always exist, given a graph G, which is simple graph, all right. They said that there must always exist a contracted graph G prime of G, such that first, the number of edges in G prime is reduced by a factor of delta, where delta is like a mean degree, is the mean degree of G. So the number of edges is reduced by quite a lot. And next is that G prime, although it's smaller, it preserves non-trivial mean cuts of G. And by non-trivial cut, I mean that it's a cut such that both of the sides contain at least two vertices. All right. So this is very handy once you have G prime, because this is a good observation. The edge connectivity of G is exactly a minimum, like a minimum, is a minimum between the two things. First, it's just the edge connectivity of G prime and a mean degree of G. Why? First, observe first that this both of these number is never an underestimate of edge connectivity. And the reason is that G prime is a contraction of G. So the mean cut, the size of the mean cut never decrease. And also a vertex with mean degree form a cut in the graph. So it's at least a mean cut. The size is at least a mean cut. All right. So we have one direction. Now let's consider two cases. Suppose that the mean cut is trivial. So one side is just one vertex. Then by definition, you have that the lambda G is the delta. And if the mean cut is non-trivial, we know just by the guarantee of G prime that G prime preserve a non-trivial mean cuts in G. So here the edge connectivity must be preserved. So that's it. It's a handy thing to have. So now once we have this, an algorithm by Gabao fit perfectly into this because it can compute, actually given any graph G prime, might not be this graph G prime, but any graph G prime with another upper bound, delta, you can compute, this algorithm can compute the minimum between the edge connectivity of that graph G prime and the upper bound in this time, the number of edges G prime of G prime times the upper bound. But now once you plug in this G prime with this guarantee, this time is exactly just linear in M. So it means that given G prime, you are done. You get the edge connectivity in linear time. Now what we will do is that we will compute G prime in almost linear time. And the size of our G prime will be also not exactly M over delta, but like with some overhead, and that overhead is subpolynomial term. But with this small overhead, once you have G prime, just plugging in Gabao, you can compute lambda G in M gamma time as well. And that is what we are gonna do. So let's try to compute this G prime. Now the setup is this. You have a graph G, simple graph, and let's see be a non-trivial mean cut. And I write a lambda as a lambda G from now. Note again that lambda is at most delta, the mean degree. Let's look at the algorithm by a quick glance. I will explain each of the steps again, but the algorithm will do the following. It will compute a collection of set of blue set here, C, and then it will for each of the blue set, it will compute a subset of purple subset. Each of the purple subset is C prime, and then each of the purple set you compute another subset here, a black one. And then G prime will be just by contracting each of the black subset. That's what we are gonna do. And we will show that each of the black subset will either contain completely in the min cut or is disjoint from the min cut. So that's why by contracting a black set, it doesn't really destroy any min cut. So G prime will preserve a min cut. So that is the overview of the algorithm. Now let me explain the details. So the first step is to do something called expander decomposition. And this is a following procedure. You are given a graph and expansion parameter where we will set it to be something like 100. Now it will return a partition called C, a partition of vertices V. Each part, I call it X for expander. And what we will have is that for each of the X expander here, if you look at any cut inside X, the number of edges crossing a cut will be at least alpha times the smaller size of the, like times the minimum between S and X minus S. All right. So that's what it does. And another thing is that the number of edges crossing the blue component is just around N, basically, where this gamma term is small and alpha will be set it to be some constant. And the time to compute is also almost linear. So that's expander decomposition. Each part, the number of each part is an expander, it kind of expand, and the number of edges crossing each part is around N. Okay, so now let's just look at some expander and mean cut C. And let's look at And let me denote S by the intersection between the two sets. I will claim that the min cut cannot overlap a lot with the expander. That is, the size of S must be at most lambda over 100. And the reason is just this. That's a proof. So you look at here, the number of edges crossing S and X is the min cut edges. So that this thing can be at most lambda. On the other hand, because of the expansion of the expander, we have that the number of edges crossing here must be at least 100 times S. Combining the two things, you get what we claim. So S cannot be too big. That's the first step. The next step is that is called trim. So given any set of vertices X, trim of X is obtained from X as follows. As long as there exists a node V in the set, such that kind of the inside degree, the number of edge between V and other node inside X, if the inside degree is smaller than 2 delta over 5, then you just remove V from X. As long as it exists a low inside degree guy, you keep removing it until it doesn't exist. The remaining part, you call it trim of X. That is, if you look at the remaining part, the inside degree here must be at least 2 delta over 5. It's just by definition of how we construct it. Okay. So that is trim of X. So let X prime be a trim of X, and S prime be in the intersection between C and X prime. Now I say that min cut can overlap only by a bit to the trim set. By a bit, I mean the size of S prime can be at most 2. And the reason is this. So suppose that is a bit bigger. S prime is a bit bigger than 2, it's 3. We will show that there is a contradiction as a warm-up. Just look at the case when it's 3. So first, again, the edges that cross S prime and S prime here, this is a min cut edges. So this is at most lambda. And now how many edges must cross? The idea is that each of these nodes here is inside the trim set, right? So there are a lot of edges incident to it, like a 2 delta over 5. But so most of them must cross because the set S prime here, if it is just 3 nodes here, there can be only 3 edges inside. So almost all of the edges must cross the min cut. So that is, and this is so what do we have? You have that there are 3 nodes. Each of them contribute 2 delta over 5. And the number of endpoint inside S prime is just at most 6. So that is greater than delta, but that is a contradiction because lambda is less at most delta. Okay, so in the general case, we know that, okay, if S prime is not less at most, if this is not true, S prime is at least 3. At the same time, we know that S prime is a subset of S, so the size is at most this also. It's not too big as well. Now, it's just the same argument. Here we count the number of endpoint that cross, endpoint of edges in X prime that cross S prime. And it must be at least these 2 numbers. You can pause and check. But the idea is really the same. As long as S prime is not too big, the number of edges inside S prime itself must be small, and almost all of the edges must cross the cut, and that will be too big. If you look at the math, you will have this number, and you have that this number is indeed greater than delta as long as s prime is between this region, which is the case, and that is a contradiction. So now the last step. The last step is that is to shave. So it's defined like this. Given x prime, shave of x prime is just a collection of nodes in x prime, such that the inside degree is strictly more than degree of the node over 2 plus 1. Just to have some to compare the two things, which is similar, trim procedure kind of keep removing low inside degree vertices recursively as long as it exists. For chef, it's just look at all vertices in X prime and just remove all of them once, but never look again for the new guy with low degree. It's just look at all of this. It's just really remove it once. Okay. So if you look at the set X double prime as a shape of X prime, then from the definition you would have this. That is, for each node in X double prime, the number of edges here that goes to from V to X prime must be at least must be more than this. This is really by definition, but I just want to note that you count the edges that go to X prime too, right? It's not you don't count. It's not just the number of edges inside X double prime itself. You count this all of this node is the one that is greater than degree of V over 2 plus 1. So now the claim is that a mean cut cannot overlap at all to the chef set. That is, if you take S double prime to be the intersection between X double prime and C, then this will be empty. So let's prove it. Suppose that is not the case. Suppose that there is some non-trivial intersection. So let that be V in S double prime. All right, and that V is also in S prime here, right? So, but we know that S prime, the intersection between C and X prime, S prime is of size at most 2. So there may exist only one more vertex V prime in S prime. So there are just at most 2 vertices in S prime here, right? But what do we have? Then I claim that the number of edges from V that cross the min cut, if you just count from V to X prime outside the min cut, that must be strictly more than the degree of V over 2 already. Why? Because the number of edges from V to X prime is more than degree of V over 2 plus 1, but this plus 1 only can go to V prime. Other things must cross the min cut. So that's why you have this inequalities. But once you have this, what it means is that this vertex V, more than half of its degree goes out of min cut. So if you just move V out of C, you get a smaller cut. And you can indeed move V out of C because C is non-trivial. And if you can do that, that's a contradiction because we assume that C is a min cut. So that is That's a proof of a key property. So just to recall again, we first compute the expanded decomposition. That's blue. We get a blue set. For each of the blue set, you trim and get a purple set. For each of the purple set, you shave and get a black set. And you contract the black set. But we claim that the black set must be, we just show that the black set must be completely disjoint from C or completely contained in C if you just flip this, if you just flip the set C to, right? So it means that the G prime must preserve non-trivial mean cuts. Okay, so now it remains to analyze the size of G prime as well, but this is a thing that also is quite easy. So, okay, now let's look at this. The number of edges in G prime is just all the edges excluding the part that you contract, right? So you can just divide it into three parts. The first part is just all the edges after you contract the blue set, the blue part here. The next part is the purple part. It's just all the edges after you contract the purple part, but exclude the blue part. And the next is the gray part here. It's just all the edges after you contract the black set, but excluding purple and blue. All right. Now the blue part is just it's just you just count all the edges that cross the clustering of the expanded decomposition, but that is just around n with some overhead factor here. And by the some simple charging argument that is shown in Kawarashi and Tora paper as well, and in my paper too, the purple part and the gray part will be within constant factor from the blue part. And with this, we have that the size of G prime is around n, and that is at most m over delta because delta is a mean degree. All right, so that's what we have. Just to conclude, the size of G prime is indeed around, is less than m by a factor of delta. The time to compute it is just around linear because clearly, except the first step of expanded decomposition, other step is just linear time. It's just so trivial. And because G prime preserve non-trivial mean cut, we have this equality, and Gabau's algorithm can compute exactly this in this time, and that gives us almost linear time. So the point of this work is that given an expanded decomposition, just by trimming and shaving, a super simple step, you can get edge connectivity easily. And I think this work is like a gentle introduction to how to use expanded decomposition. We use it in a very straightforward way compared to the how it was used in literature. So thanks a lot for listening.